Okay, good morning, Cheryl. How are you? Can you hear me? Voice check, voice check.
Hello, I can hear you. Can you hear me?
Oh, lovely. Okay, fantastic. Happy Cinco de Mayo, if you celebrate that at all. It's wonderful.
Yeah.
Yes, Cinco de Mayo for south of the border friends. All right. I thought I'd start on the next part of that homework to finish up is the BJT emitter follower. And let me ask a question, and that is, how well do you understand the function of capacitors and how they handle signals in BJT amplifiers? What is the purpose of those capacitors? Do you recall? I'm going to call up an example in a moment. Let me go ahead and pull this guy up and move this off to a different screen here. Come on, click. And come on, mouse. Okay, let me go to, for example, right here. Where's a good one to start? Let me just start right at the beginning. 279. So let's go to, I'm going to do a share screen with you in a moment, and I'll put up an image for you and we can talk about this. So let me go ahead and share screen first.
Okay.
There. Okay, so here's my OneNote. Oh, wait, come here. There's my OneNote. And here, let me do a snip. And let's snip this guy out. And let me paste this in here for us to look at. Okay, can you see this transistor?
Yes.
Amplifier. Okay. And as we're looking at this transistor amplifier, let me get my pen. Do you know the function of C1 and C2 and C3? What are they called other than capacitors? Can you call them, do you know how to name them based on their function? Yes, they are capacitors, but what are they doing in this circuit?
I'm not entirely
It's okay.
sure.
It's okay, because this may not, there's a lot of background information I'm going to help you out with. And so this may not have been explained to you before. Your C's, caps, do this. They block DC and pass AC in signal amplifiers, which is really significant. We have to understand that very, very important premise of what capacitors do in signal amplifiers. Capacitors have a variety of different functions used in all different kinds of circuits, but used specifically in signal amplifiers, they do this. Now, why do they block DC? There's a purpose. Block DC to contain DC voltages and currents from adversely affecting your AC source and signal output. I'm sorry my writing is so scribbly, but I'm writing with this goofy little pen on a slippery screen.
That's okay.
I'm writing the best I can. Okay, but you'll get a recording of this so you can review it at your leisure. So it blocks DC to contain the DC voltages and currents from adversely affecting the AC signal source and signal outputs. So let's go ahead and highlight where those are. They happen to be here. Here's C1, and here is C2, C3, and here is C2. Okay. And as we look at this, it shows this particular illustration shows the signal in, and so we happen to have here signal input is right here. And if you take a look at RL, the L stands for what? Do you remember?
Load.
Excellent. So the load is typically attached to your output. And so therefore, if you look at the load resistor, it's attached to a point that's called V out. And V out is typically where you could hook up an oscilloscope and measure the signal there. You can measure the signal there, or you could also measure the signal here. You can, and this particular point would be called the collector. This node is called the emitter, as you know, and this node here would be the base. And we can measure at either of those two places. But when we measure at either of those two places, the waveforms on the output tells you everything. Remember, C3, like all capacitors, they block DC. There is no DC on the right side of the capacitor. So when we're measuring our signal out after the capacitor, you have 0 volts. That signal, that waveform, the blue waveform, is riding on 0 volts. Whereas if we measure at point C, right at the collector on the left side of the capacitor, there's DC there. There's all kinds of DC happening within that transistor because we have a DC source right there, okay? And the DC source provides the biasing, which turns on the transistor. And so on the left side of C3, we have some DC voltage, which is revealed right here. And we can easily calculate that amount of voltage. That's no big deal. But when we go to measure this on an oscilloscope, we have to realize that there is a fundamental difference between these two waveforms. That the first one is called signal riding on a DC reference level of 8.20 volts DC. And so when you look at that on an oscilloscope, it won't, depending upon how you set up your oscilloscope, you should be able to see it, or you can also choose not to see it. And that's a lab thing that we can talk about in a lab situation. But if we measure in those two places, V out, and let's call that point X. Let's call that point X right there, X. We will see the waveform that's shown on the right, on the lower right. If we measure with our oscilloscope at point C, we will see the waveform on the output shown in the upper right. And so capacitors, you can see here, truly do block DC for the purpose of what? Containing the DC voltages and currents from what? Adversely affecting the AC signal source and outputs. Okay, another thing to keep in mind here is this. Another very important concept is right here. All AC signals will see DC sources as ground. And we'll hold that thought. We'll come back to it. It's something that's pretty important that will help you understand how these things amplify and how they will process signals, but they will see this as a ground. All right, so that being said, let's talk about, Actually, this is probably better done this way. Let me go ahead and not rely on my penmanship. Do you understand the differences between common source, common drain, and common emitter configuration amplifiers?
I think there's two of them together, and then they're both connected input to output for one of them, either the drain or the source or the gate.
Okay, all right. So let's go back to some fundamentals here that'll help you out, because there's some very specific characteristics that are common between transistors as well as MOSFETs, JFETs, MOSFETs, E MOSFETs, DE MOSFETs. They all behave in a similar fashion. But let's start off with this. Let me go ahead and change the size of the type. Okay. Configurations of signal amplifiers. And this will pertain to, let's see, BJTs and our MOSFETs. Okay. I'll do this, slide into here. All right, so here we go. To determine which configuration is being analyzed, number one, find input lead of transistor, find output lead of transistor. And as you can see, I'm abbreviating transistor with the abbreviation I showed you yesterday. The X is a X equals abbreviation for TRANS. Okay. All right. So find the output lead of the transistor, and here you go. Left over lead is the name of the configuration of amplifier. Okay, so those are the rules. And why do I have this guy here? Don't know. Okay, so if you take a look at this picture that I'm showing, can you determine of the three leads, base, collector, emitter, which is the input lead? Because that's the first thing that you need to do in step number one. Let me do an undo. I just messed things up. Okay, so as we look at this picture, which is the input lead? Call out the lead.
Input lead.
Generally on the left. Look at the waveform, see the blue arrow, and what's the blue arrow pointing to?
The node.
And the node
right
is attached to
after
which lead? Is attached to which lead of the transistor? I wrote down B.
B.
Yeah.
Okay.
I wrote down B in red. That's your base.
It's attached to B?
Yeah, the signal is attached to the base.
Okay.
Okay, signal is attached to the base. And now take a look at the output waveform. The output waveforms are attached to which transistor lead? That's on the right-hand side. And look at the
The
waveform.
C.
The C, and the C is which lead? That's called the, C stands for?
E is emitter.
Yeah, E is emitter, you got that.
Base
Collector.
emitter. Collector. Yeah, they have a different word for BJT than MOSFET and.
Yeah, no, I understand. Yeah, at the upper lead for a MOSFET would be a drain, and then you have a gate on the left, and you have a source on the bottom. But they all work the same. So we'll start with this, since it happened to have the pictures for it. So we have a collector. So if the signal goes in the base, so the input lead turns out in this particular case to be the base. And the output lead here turns out to be the collector. Then what is the leftover lead that has no signal attached to it?
The emitter?
The emitter, precisely. And this is the emitter. So since this is the leftover lead, this is called, the name of this, oops, come back here. Oops, there's my cursor. Here's my cursor. Over one, enter, enter, is called common emitter configuration of amplifier, otherwise known as CE config. Okay, and this has some very, very specific properties. It happens to have AV is high, and it also happens to have a I, I'll do it this way, AI is also high. And it also has an AP, which is highest. And it also has phase inversion. It's the only one that has phase inversion, and there's reasons why there is. We won't get into the weeds of that right now. Okay. Now, we'll hold those properties as a thought, because I'm going to show you one that is pertinent to our task at hand. And I want to go to 292. So let me go to 292 right here. Now let me snip this guy out. There's my snip tool. There's my snip. Snip now. And here we go. Right here. And let me paste this guy here. Paste. And let me make this guy bigger. Okay, we're going to do the same 3 steps. Copy. And let me paste this right here. Boom. Okay, you call it out now. The input lead of the transistor, the output lead of the transistor, leftover lead is the name of the configuration. You can do it. Is there a signal here that's marked V in? And is there a signal on the right-hand side called V out? Remember, the input's on the left-hand side, going in, and the signal coming out typically drawn on the right-hand side. So this is going into which lead of the transistor? Very similar to the one up above. What's that middle lead of the BJT called? base, which on your FETs, will be commonly known as the gate, okay?
Oh my goodness, I'm so sorry. I didn't realize I was muted. I was
Oh,
talking.
I'm sorry.
I'm so
Yeah.
sorry. I had background noise, so like I kept hearing beeping and I didn't want it to interfere, so I muted myself.
Oh,
But I meant to say base and then
okay.
gate.
Yeah, so it would be in, yes. So in FETs would be equivalent to going into the gate. Now, where's the signal coming out?
It's coming out from the emitter.
Precisely. Okay, so let's go ahead and name these now. So the input lead is going to be the base, or in a FET would be the gate. And the output lead in this particular case is the emitter, which in a FET would be the source, yes?
Yes.
And then the leftover lead is what?
The let's see again. Wait, I'm trying to try to remember it.
Right here.
Collector. That's what it's called, collector.
Collector, okay. So collector, which in a FET would be the drain.
Drain.
So the leftover lead is the name of this configuration. So how would you name this particular, one?
The leftover lead. That's common source amplifier.
Where the leftover lead. The leftover lead is the name.
Leftover lead. Common collector?
Exactly.
Oh.
The leftover lead is the name of the configuration of the amplifier. Common collector, configuration, amplifier. And it also has very specific characteristics. It has an AV that is equal to 1. Oops, meant to say equal to 1. It has an AI that is highest. It has an AP that is moderate. And it also has no phase inversion. And it's typically called a follower. Okay, and that would be either, let's go here, follower, either an emitter follower or a drain follower. Signal amplifier, boom. We'll explain this one in greater detail after I show you one more, okay? Because you need one more to round out the 3 different configurations of signal amplifiers. Next one.
Okay.
299. So let me go to here. 799. Okay, here we go. And I'm going to snip now. All right. And we're going to do this one from here to here. All right. And paste this guy right there. And let me make this bigger so that you can see it. And let's copy these 3 questions. Copy. And let's paste these down here. Paste. Oops. Maybe I didn't copy it properly. Control C. And come on. And all right, there we go. All right, call it out, Cheryl. Find the input lead. Follow that wire. Where does it go?
To the middle one's the base, the bottom one's the emitter. That's the emitter.
Mm-hmm. So the input lead in this particular case is the emitter. Never had that before. Okay. Output lead.
The collector.
Collector. All right. Calling it out with confidence now, see? And therefore, what is the leftover lead?
The base.
Aha. Base. So as this is the base, so this has a name. This would be called common what?
Common base amplifier.
Configuration amplifier, correct. And this has very specific characteristics. It has an AV that is, of the 3 different ones, the highest. It has an AI that is equal to 1. It has an AP that is moderate. And it has no phase inversion. So these are very important concepts so you can very quickly recognize what kind of configuration the amplifier is, and therefore you can determine which of these characteristics are going to come to bear. So let's go ahead and collect all this information and summarize this so we have it all in one place, okay? So let me come here, hit a snip. I want to collect this information and we'll paste it right down here. Boom. And then we'll collect this one. Come on, mouse. Here, snip. And paste this down here. And then snip this information here. Nope. And paste this underneath all of this. All right. And on each one of these, let's take a look. Help you out. Move this guy down. Select this one. Oh, come here, this one. Move this guy down. Cool. Oops. Okay, and then we'll give you a nice summary diagram. Select this guy. And I'm just going to jam it in here and shrink this guy up and place this up here. So we can see a version of this right next to the description, okay? And then we're going to do the same with this guy, because I want these all in one place for you.
Okay.
Okay. Snap this, put it in here, reduce this, and put this up here. Okay, good place for it. And then the final one, this one here. Copy, and we'll paste this right down here. Okay, we'll have our summary diagrams right next to our descriptors. Okay, so now we can see all three of those, all right? And with their descriptors. So what we have here is your CE. What we have here is your CC, configuration common collector. CC. What we have here is your common base configuration, known as CB. And they are associated with their matching FET counterparts, that this would be your common source, this would be your common gate, and this would be your common drain. Let's see, hold on a sec. This would be your common gate, sorry, and got excited. This would be your common drain, red. There we go. All right, so now that being said, why do we have in your exercise this thing called an emitter follower? All right, so let's take a closer look at this particular one. And let me go to 94. Oop. 294. Okay, so let's go ahead and snatch this particular one here. Where's my snip? Here's the snip. Boom. Okay, now let me grab this guy. And let me paste it right in here. So what we're doing with this particular one is applicable to FETs as well. All right, so given this particular circuit, call out input lead, output lead, name of configuration. So here, input lead equals blank. Output lead equals blank. Config, spell it correctly. Config equals blank. Okay, help me fill in the blanks.
The input lead is the base.
Clearly, good job. Okay, base.
The output lead is the emitter.
Emitter, good job.
And the config is the collector.
Common collector.
Oh, common collector.
Yeah, the leftover lead is collector, you're right, but we have to name the configuration as common collector. Common collector, or otherwise known as CE config amp. Okay, were there some specific characteristics pertaining to a common, I wrote it down wrong, sorry. Got excited again. Were there some very specific, yes, characteristics pertaining to a common collector amplifier with respect to AV, AI, power, and phase inversion. Let's go ahead and look at our summary. What do you see?
No phase inversion.
No phase inversion. Voltage gain is what? Voltage gain is AV is?
Change in output over, 1.
Oh, it's 1. It's simply stated, summarized as 1. Current gain is?
Highest.
Highest. Power gain is?
Moderate.
And there's no phase inversion, as typically called a follower circuit, yeah? All right, so what we're gonna do is to reiterate those characteristics. So AV equals 1, AI equals highest, AP equals moderate, and no phase inversion, no inversion. Done. Now, if we go to analyze this mathematically, because you're asked to derive some sort of rationale for why the gain ends up as it is, and then you're asked to offer rationale as to why it's called the follower circuit. And so if we go to analyze this particular circuit, you may or may not have been given this formula that your AV is equal to RE over R prime E plus RE. Have you seen that gain formula for this amplifier before?
I don't think I recognize that, no.
Okay, that's all right. That's all right. That's all right. That's all right. This is all helping to explain why this guy is called the follower circuit. So I'm just going to go through a quick analysis of this with you, okay? All right, so if the signal comes in, here's the signal. Signal comes in here. The signal will go through the capacitor because the capacitor will pass AC signals. We said this way at the very beginning of the session, right here, that the caps will block DC, but they will pass AC in signal amplifiers. So that they are there to contain the DC and allow the signal to come through. Now, the other summary, a very important statement, is this guy here. We come back to this guy now. All AC signals will see DC sources as ground. I wrote it down. I said we would come back to it. This is significant to help you understand what's happening on the input side. So, which way does the signal flow in this particular case? The signal will flow on the input side. It will flow up because it splits at this node. It will go down. So the signal will come down to ground. Yes, that's one path. Another path for the signal to flow is to flow directly to the DC source because it thinks of the DC source as if the DC source were a ground. Okay, so that's another path. There's a third path, and that is to go directly into the transistor. So as the signal can go directly into the transistor, this is what happens on the input side. On the output side, let's see what happens on the output side. On the output side, the signal can come up here and go here and go to the DC source as ground. The signal can come down here to this node. Once it hits this node, it can split. Part of this can look like it's going this way. Part of it looks like it's going this way. So your signal source coming in is shown in the yellow arrows, and your signal sources on the output are shown in the green arrows. So let's analyze the RE portion of this guy first. The RE portion of this guy, and notice that's written in a little lowercase e, is actually going to be your emitter resistor in parallel with your load resistor. Aren't these two resistors, this guy here, RE and RL, are they not in parallel with each other? They both meet right here at a node called emitter. So they both meet at the emitter, and they both connect to ground. So if the top of these guys are connected to E and the bottom of these guys are connected to ground, therefore they are in parallel with each other. Yeah?
Yeah.
Can you calculate the parallel relationship between those two? What's my resulting ohms?
Sorry, 1 second. I'm gonna grab my calculator real quick.
Okay. So you have 470 in parallel with 470.
Yes, so it's 470 times 470 divided by 470 plus 470, which is
235 ohms?
235 ohms.
Okay. I'm not brilliant. There happens to be a shortcut. You were doing product over sum, okay, which is fine. You were doing RE times RL over RE plus RL, and that is known as product over sum, and nothing wrong with that. There is another shortcut. Another shortcut is known as Rx divided by N. And this applies to parallel of same values. Do I not have a 470 on the left for RE? Do I not have a 470 on the right for RL? Are they the same values?
Yes.
Cool. So as long as you have resistors in parallel of the same value, you simply take that value, 470, divide by the number, N is the number. How many resistors of the same value? 2. There, shortcut. And you could do that with Mama's calculator. You don't even need your TI-84, right?
Nope.
I call it Mama's calculator. It's a nickname. I joke with all my students that it's your God-given calculator that mom and dad gave you between your ears. So if you're let's say you're at Macy's, or you're say Abercrombie and Fitch, or wherever young people go shopping for clothes, and you see this glorious, outrageous looking pair of pumps, and you just got to have it, and this $470. But all of a sudden the clerk comes and puts down half off. Boom. Do you need to pull out your TI-84 and calculate half of $470? The answer is no. You can do that in your head. And you did that with Mama's calculator, right?
Yeah, right.
Okay, there you go. Yeah, so you don't always have to reach for the calculator. Well, if you're doing product over sum, yes, you're gonna have to reach for your calculator. But if you know this other shortcut, the Rx over N shortcut, and that applies to anytime we have same values, just boom, take that value and put it over the number of resistors that have that same value, and there's your answer. So we end up with 235, done. All right, I didn't mean to go so long into this. Okay, now, then there is also right here a very important quantity called R in at the base. And R in at the base is very important. We need to know those ohms because we know R1, yes, we know R2, but we need to know R in base because that's the third part of how the current splits on the left-hand side. So your R in base is very simply given as your beta AC, and this will be times your little RE, your R little e, which we calculated a moment earlier. And so this particular one here, you assume, or you're given given your beta AC equals 175. So that's your given as a parameter. So in this particular case, this would be 175 times 235. Give me a number.
235. Oh, I input it wrong. 41.125 times 10 to the negative 3, which was kilo ohms.
Okay, girl. Oops. Ah, what happened? No, I don't want to. Go away, go away, go away. Cancel, cancel. K equals kilo does not equal kilo. Okay, you might have a kilo pair of pumps, but you don't have a kilo pair of pumps. Okay, so let's not call it kilo, it's kilo. All right, so you're right, it's 41.125 kilo ohms. Okay, that's an important number. Now, the next thing is we're going to need to know how much input total. In total, you have 3 different paths that the current is splitting. You see the yellow arrows on the left. Part of it goes up, part of it goes down, part of it goes into the RN base. So you have 3 different paths for current that are all in parallel with each other. And this works out very simply as R1 parallel with R2 parallel with your RN base. Okay, so let's go ahead and pop these numbers in. Your R1 was 18 kilo and then 51 kilo. So we have 18 kilo ohms parallel with 51 kilo ohms parallel with your newly calculated 41.125 kilo ohms. Now, when you do this calculation, 18 reciprocal plus 51 reciprocal plus 41.125 reciprocal equals, what do you get?
99 point
No.
4,
Okay, you
eight.
have to hit reciprocal one more time.
Huh?
You have to hit reciprocal one more time. Whatever number's on your calculator, you needed to hit reciprocal one more time.
10.05 ohms. Or
What
kilo
are the
ohms.
units? Yes, that's right.
Or kilo.
Kilo ohms. Very good. All right, so that's your RN. So that's the input side. This is really, really important. We have to know what's going on the input side. And so here we go. What we can do here, what we need to do next is this. We now know that we can do this. We said that the voltage gain is 1, yay? For this particular configuration of amplifier. We said earlier that the voltage gain right here was AV is equal to 1. Well, let's go ahead and prove this to ourselves by doing the following. Can we determine what type of signal we would have at the collector? No, let's see, at the emitter. Yeah, what type of signal do you actually see at the emitter? And we can do that very, very quickly. shrink this up just a touch. All right. So the DC calculations for this are right here. Your voltage at the emitter, signal at the emitter, is equal to your R2 over R1 plus R2. And you multiply that by your source voltage, and you subtract your BE junction voltage. Looks really complicated. It ain't. You're calculating a voltage divider between R1 and R2 to find the voltage at the base based on 10 volts at the top. And so therefore, this will work out to be, let's see, 18 kilo over 18 kilo plus 51 kilo. And then that will multiply by our source of 10 volts and minus 0.7 volts. If you go to do the math for your VE, trust you will, let me go ahead and do that with you. Let's go ahead and take 18 divide by open parentheses, 18 plus 51 close parentheses, and then times 10, and then subtract 0.7. Okay, you should have a number.
12.419 kilo ohms.
Oh, we're calculating a voltage.
Oh shoot.
Yeah. So you have to do
volts.
the 18.
Yes. No, wait, that would be. I think I did something wrong. Is it?
Oh, let's see. So 18 divide by open parentheses, 18 plus 51, close parentheses, equals this. And then let's do times 1,000, and then times 10.
I don't think I got the exact, I typed it in exactly the
Oh,
same
I'm sorry.
way, but
I apologize. I apologize.
I got 1.908 though.
Yeah, I totally apologize. I popped in the wrong one. I wrote down R2. It should be 51. So 51 over 18 plus 51. I totally apologize.
Okay.
So 51, 3, divide by, open parentheses, 69, exponent 3.
6.69 volts.
And minus 0.7, we end up with 6.69 volts. Perfect. 6.69 volts. Very important voltage at the emitter. Now, how about we determine IE? IE is going to be equal Ohm's law, VE over RE. So VE is your 6.69 volts that we just did, and the RE in this case, 470 ohms. So pop me out a number there.
14.23 milliamps.
Amps, correct. And now another piece of the puzzle is this little tiny R prime E. And this is a constant. The constant is 25 millivolts over IE, okay, that we just calculated. So this is a constant. So if we go to pop this in, watch, This will be 25 millivolts over 14.23 milliamps. Let's go ahead and make that calculation. 0.025 divided by
1.757.
Okay, so if we use your calculator's memories, it will come out to be 1.76 ohms. Tiny, very tiny, but is significant. Very, very significant. All right, so we now have these ohms. And now the magic. Watch this. Your AV, we stated earlier, is equal to R little e over R prime E plus R little e. If we go to put this all together, we calculated our 235 ohms. And now this is equal to 1.76 ohms plus the 235 ohms. So this will give you 235 over 236.76 ohms. This will be 0. Let's do this. So 235 divided by 1.76 plus 235, close parentheses, boom. What do you have as a decimal?
235 divided by 236.76. 992
Yeah. Milli.
Milli.
Yeah, 992 milli. Okay, so this is not in volts. This is not in ohms. This is an AV. This is a voltage gain. Voltage gain. And it's less than 1. That's how we prove that the AV is approximately 1. AV is approximately 1. And because it is approximately 1, actually you lose a little bit along the way. That's why we have signal at emitter follows the signal input at the base. That's why these are called emitter follower. That's your rationale, which will be the same as if it's an emitter follower, then that would be a drain source follower. And let me double check that upstairs. Drain, hold on one sec. We have drain out on the source. Oh, common drain follower. Drain follower, what did I write down before? Okay, because our drain is on top, source is on the bottom, and common drain. So this would be drain follower. Oop. Don't often use the term, but there you go. It's another follower circuit, and that's why you have signals of why your gain is going to be 1. That should answer your question number 2 on your homework. Okay, took a little bit to get to this point. I will save these notes for you. The recording of the session will be saved, and I'll set you up with a link to that particular recording so you can review this at your leisure. I know you have another Zoom you need to get to at 11 o'clock, yeah?
Okay, yeah.
Okay.
I'll get going then. Thank you so much.
All right, Gail.
All right.
All right, you have a
Bye.
good one. Take care. Bye.
Thanks. Bye.
You're welcome. Bye-bye.